For most of modern astronomy, the smallest worlds in our solar system were treated like leftovers, frozen debris, failed planets, ancient objects too small to become anything interesting. Then spacecraft began reaching them. In 2015, NASA's Dawn spacecraft approached Ceres, a tiny world hidden among millions of objects in the asteroid belt. As its cameras sharpened, something appeared inside one of its craters, brilliant white patches. They were so reflective against the surrounding terrain that at first, scientists could not explain what they were seeing. Years of observations eventually revealed something even stranger beneath them. Ceres had evidence of briny liquid beneath its frozen surface. And it was not alone in breaking expectations. Far beyond Neptune are worlds stretched into bizarre shapes, worlds with rings where scientists once thought rings should not survive, and objects following enormous orbits that carry them into regions of the solar system we have barely explored. Some are so distant that sunlight takes hours to reach them. Others have remained almost unchanged since the earliest days of planetary formation, preserving material from before Earth became the world we know today. And astronomers suspect we have found only a fraction of them. More than 100 additional objects could eventually qualify as dwarf planets, scattered through a vast region of darkness beyond Neptune. Some may hide oceans, some may preserve chemistry billions of years old, and some follow paths through space that are still difficult to explain. These are not simply miniature versions of planets. They are survivors from the construction of the solar system itself, each carrying a different piece of the story that the larger planets erased long ago. And the farther astronomers search, the stranger that story becomes. If you're settling in for the night with this one, take a second to like the video. It's a small thing, but it helps more people find their way here. The story begins with a category of worlds that astronomers did not realize they needed. For most of human history, the solar system ended where our eyesight failed. Mercury, Venus, Mars, Jupiter, and Saturn could be followed without telescopes. Later instruments revealed Uranus, Neptune, and increasingly faint bodies beyond them. Yet the immense region past Neptune remained poorly populated on our maps. Astronomers suspected material might survive there, but direct evidence was remarkably difficult to obtain. That changed in 1992. Jane Liu and David Jewett detected a faint object moving against the background stars. It received the designation 1992 QB1. The object traveled beyond Neptune, where years of patient searching had produced almost nothing. Its discovery confirmed that Pluto was not alone in this distant territory. More detections followed. At first, each appeared as little more than a moving point of reflected sunlight. Together, however, they exposed an enormous population. We now call this region the Kuiper Belt, a broad reservoir of icy bodies left from the formation of the solar system. Some are tiny fragments. Others possess enough mass for their own gravity to shape them into rounded worlds. That distinction became important as discoveries accumulated. By the early 2000s, astronomers were finding objects large enough to challenge the familiar planetary roster. Eris intensified the problem after its discovery was announced in 2005. If Pluto counted as a planet, scientists had to decide whether Eris, and potentially many additional bodies, deserved the same status. In 2006, the International Astronomical Union adopted a formal definition. A dwarf planet must orbit the Sun, possess enough mass for gravity to produce a nearly round shape, and remain gravitationally subordinate within its orbital neighborhood. It must also be something other than a moon. The phrase clearing the neighborhood can sound more dramatic than the process itself. Over immense spans of time, a major planet becomes gravitationally dominant along its orbit. It may absorb smaller bodies, scatter them elsewhere, or control their motions through repeated encounters. Dwarf planets have not achieved that dominance. They travel among populations of other objects occupying the same broad regions. Five bodies currently hold official dwarf planet status: Ceres, Pluto, Eris, Haumea, and Makemake. Yet those five do not represent a complete census. More than 100 additional objects may eventually satisfy the physical requirements, although determining their shapes from such distances remains difficult. This changed the map we inherited. You can picture the familiar planets as only the largest landmarks within a much richer system. Between Mars and Jupiter sits Ceres. Beyond Neptune, countless icy bodies occupy overlapping paths, resonances, and distant populations that were effectively invisible until modern surveys reached them. Pluto and Eris became famous through the debate over planetary classification. The smaller confirmed worlds received less attention. Their status may sound like taxonomy, but the category opened a scientific doorway. Once we recognized these bodies as worlds rather than background debris, their surfaces, interiors, histories, and unusual behavior became part of the planetary story. On the first night of the 19th century, Giuseppe Piazzi noticed a star that refused to stay put. From the Palermo Observatory in Sicily, he recorded its position on January 1st, 1801. When he looked again, the point had moved. Piazzi continued tracking it for 41 days, measuring its path against the fixed stars. The movement revealed an object orbiting the Sun between Mars and Jupiter. Piazzi named it Ceres, honoring the Roman goddess of agriculture and Sicily's ancient patron deity. Astronomers initially treated the discovery as a new planet. For roughly half a century, Ceres appeared in astronomical texts alongside the other known planets. Then its neighborhood became crowded. Pallas was discovered in 1802, Juno followed in 1804, then Vesta in 1807. Additional bodies accumulated as telescopes improved. Instead of one substantial world occupying the gap between Mars and Jupiter, astronomers were uncovering a broad population of smaller objects sharing similar territory. Ceres gradually received another identity: asteroid. For roughly a century and a half, that description shaped how scientists viewed it. Ceres became the largest member of the asteroid belt, important primarily because of its size and position. Its classification changed again in 2006 when the International Astronomical Union recognized Ceres as a dwarf planet. That makes Ceres unusual even among its official companions. Every other confirmed dwarf planet travels through the distant regions beyond Neptune. Ceres remains between Mars and Jupiter, orbiting the Sun at an average distance of roughly 257 million miles. Its dimensions are substantial for an asteroid belt object. Ceres measures roughly 584 miles across, large enough for gravity to shape it into an almost spherical body. If you could gather the entire asteroid belt together and weigh it, Ceres alone would contribute roughly one-third of that mass. Yet Jupiter prevented this region from developing very differently. The giant planet's gravitational influence repeatedly disturbed the material orbiting nearby. Collisions and orbital disruptions kept much of that material from assembling into a major planet. Ceres survived as the largest intact body within a region where planetary growth never reached completion. From Earth, little about its appearance suggested complexity. Its surface reflected relatively little sunlight. Telescopes showed variations in brightness, while later observations indicated a landscape dominated by dark material and impact scars. For generations, we could determine its orbit far more easily than understand its geology. That limitation shaped its reputation. You could know where Ceres would appear in the sky years ahead, while remaining almost completely ignorant of what covered its ground. Then, in September 2007, the Dawn spacecraft left Earth. Powered by ion propulsion, it eventually entered orbit around Ceres in March 2015, becoming the first spacecraft to orbit a dwarf planet. 2 centuries after Piazzi watched a wandering point cross his telescope, humanity finally saw Ceres as a landscape. Against Ceres's charcoal surface, the first detailed images contained something almost unnaturally bright. Two concentrated patches appeared inside a large impact basin. As dawn drew closer during early 2015, those patches became intense enough to overwhelm parts of its imaging system. Sunlight was reflecting from material far brighter than the surrounding terrain. The location was Arrokoth crater, roughly 57 miles wide and about 22 million years old. At its center lay the brightest deposit, later named Cerealia facula. Farther east, a collection of smaller deposits became Venalia faculae. From a distance, their composition remained uncertain. Ice was possible, salt was another candidate. Public speculation produced jokes about alien headlights, while researchers worked through explanations that could survive the growing stream of measurements. Dawn kept descending. During more than 3 years around Ceres, the spacecraft photographed a crater from increasingly revealing angles. Near the end of its mission, Dawn passed within roughly 22 miles of the surface. Features once compressed into bright pixels became fractured terrain, deposits, ridges, and structures shaped by processes beneath the crust. By August 2020, several research papers using dawn data had assembled a compelling explanation. The brilliant material was dominated by salts, particularly sodium carbonate. More importantly, evidence indicated that some of those salts had risen from a deep reservoir of brine, meaning water containing dissolved salts. The impact that excavated a crater had fractured Ceres deeply. Those fractures created pathways through which underground liquids could migrate upward. Evidence from gravity measurements and geological modeling pointed toward a reservoir roughly 25 miles beneath the crater, with brine potentially extending across a much broader underground region. Once this liquid approached the exposed surface, conditions changed dramatically. Ceres has almost no atmospheric pressure to keep water stable there. Water escaped, while dissolved minerals remained behind. Repeated episodes deposited sodium carbonate across the crater floor, producing the pale material Dawn observed. Some deposits were surprisingly young. Estimates for portions of Cerealia facula place their formation within roughly the last 2 million to 9 million years. On a world more than 4 billion years old, that means material reached the surface relatively recently. Evidence also leaves open the possibility that briny activity persists beneath Ceres today. Arrokoth contained another clue. Researchers identified rounded hills resembling pingos, landforms created when subsurface water or ice pushes ground upward. Similar structures are known from Earth and Mars. Their presence here gave us another way to read the movement of buried water through an alien crust. And a crater was only the brightest example. More than 300 reflective patches have been identified across Ceres. You can trace them through numerous craters, where impacts exposed or mobilized salt-rich material from below. What appeared through early telescopes as a dark, uncomplicated body was carrying a widespread record of water moving beneath its surface. On Earth, sodium carbonate often gathers where water chemistry becomes extreme. Lake Magadi in Kenya and Mono Lake in California are alkaline environments rich in dissolved salts. Their waters can challenge many familiar organisms, yet specialized microbes flourish there. That earthly comparison gives Ceres' mineral deposits an intriguing chemical context without making them evidence of life. The deeper story lies underground. Current models describe Ceres as a differentiated world, meaning its interior separated into layers as materials shifted according to density. Rock concentrated deeper inside, while a mantle rich in ice and hydrated minerals developed above it. Water, ammonia, salts, and carbon bearing compounds became incorporated into this interior during the dwarf planet's early evolution. Ceres once had considerably more internal heat. Radioactive elements trapped within its rocky material released energy as they decayed. During the early solar system, that process could have warmed portions of the interior enough to maintain liquid water for extended periods. Models suggest Ceres may once have supported a broad subsurface ocean, increasingly salty as the world cooled and much of its water froze. Chemistry adds another layer. Dawn detected organic molecules, compounds built around carbon, in several regions on Ceres. Particularly strong concentrations were identified near Ernutet crater. Later analyses expanded the known distribution, suggesting organic material is more widespread than early measurements indicated. Organic chemistry alone does not establish biology. Such molecules can form through entirely non-living processes and are common in primitive solar system material. Still, when you place carbon chemistry beside water, salts, and a long-lived source of internal energy, Ceres becomes scientifically valuable for studying habitability. Research, published in 2024, examined how that ancient environment may have evolved. The work indicated that early Ceres could have maintained chemical and thermal conditions potentially suitable for microbial organisms within its interior. Any habitable interval would have belonged mainly to its distant past, when radioactive heating supplied considerably more energy than it does today. We have never sampled that environment directly. Dawn ended operations in October 2018 after exhausting the hydrazine fuel needed to control its orientation. The spacecraft remains in orbit around Ceres, preserved in a trajectory designed to avoid contaminating the surface for decades. No lander has followed it. No instrument has drilled through Cerean ground, collected fresh salts, or examined subsurface material in a laboratory. Everything we know comes from remote measurements, gravitational data, spectroscopy, imaging, and models constrained by Dawn's observations. That leaves Ceres in an unusual position. It is relatively accessible compared with worlds beyond Neptune, with mission studies showing journeys lasting several years are practical. More importantly, its geology demonstrates that sunlight is only one way to sustain liquid environments. A small world, hundreds of millions of miles from the sun, can preserve water through internal chemistry, dissolved salts, and lingering heat, turning an asteroid belt body into a laboratory for understanding where habitable conditions can exist. Neptune does not mark the edge of the solar system. Beyond its orbit, the architecture changes. The major planets are behind us. Sunlight weakens dramatically, and an immense population of frozen bodies occupies a broad region around the Sunday. This is the Kuiper Belt. Its inner boundary lies near 30 astronomical units, with 1 astronomical unit representing the average distance between Earth and the Sunday. The main belt extends outward to roughly 50 astronomical units. Rather than forming a narrow ring, it contains overlapping populations with different orbital inclinations, eccentricities, and gravitational relationships with Neptune. For decades, astronomers debated what might survive there. In 1951, Gerard Kuiper examined the possible history of objects beyond Neptune. He argued that a primordial population could once have existed, while suggesting planetary perturbations might have removed much of it. Other researchers proposed that distant icy remnants should remain. Direct observation eventually settled the larger question. The discovery by Jane Liu and David Jewett in 1992 demonstrated that substantial objects occupied this territory. Surveys expanded rapidly afterward. More than 2,000 Kuiper Belt objects have since been catalogued, while estimates suggest hundreds of thousands of bodies, larger than several dozen miles, may inhabit the region. Smaller objects could number far higher. Calling this the frozen counterpart of the asteroid belt misses its scale and composition. The asteroid belt occupies a relatively compact region between Mars and Jupiter. The Kuiper Belt begins billions of miles farther outward and spreads across an enormous volume. Its members also preserve materials that could not remain exposed as ice much closer to the Sunday. Temperatures commonly fall between roughly -364 and -400 degrees Fahrenheit. Water behaves as solid ice. Methane, nitrogen, and carbon monoxide can also freeze onto surfaces under appropriate conditions. Sunlight provides little warmth, allowing volatile substances, materials that readily vaporize at higher temperatures, to survive for immense spans of time. Even communication reveals the distance. Depending on where an object lies, sunlight can require several hours to reach it. A radio command sent from Earth faces the same fundamental limit imposed by light speed. Exploration, therefore, unfolds without immediate control from home. When we look into this region, we are also looking toward material that escaped much of the heating and geological processing experienced closer to the Sunday. Many Kuiper Belt bodies preserve ancient ices and organic compounds dating from the earliest stages of planetary formation. Their surfaces have still been altered by radiation, impacts, and seasonal changes, but their deep freeze can retain chemical evidence lost elsewhere. You might imagine the familiar planets ending in open emptiness beyond Neptune. Modern astronomy gives us a different picture. The outer solar system contains resonant groups locked into repeating gravitational rhythms with Neptune, dynamically excited populations on tilted paths, and bodies scattered onto elongated orbits. Among this population orbit Haumea and Makemake, while more distant objects extend the known system farther outward. Here, planetary science becomes an investigation of worlds assembled from ancient ice, rock, collisions, and preserved chemistry, occupying territory that telescopes only recently learned to map. Imagine trying to draw Haumea from observation. Before outlining its surface, you would encounter a basic problem. Its apparent brightness rises and falls dramatically within a few hours. That repeating pattern gave astronomers one of their first clues that this distant body had an extraordinary shape. A day on Haumea lasts only 3 hours and 55 minutes. During one Earth day, the dwarf planet turns more than 6 times. Even Jupiter, the fastest rotating major planet, requires just under 10 hours for a rotation. Haumea is therefore spinning at an exceptional rate for an object of its size. That rotation changes its entire figure. Gravity naturally pulls large bodies toward spherical shapes by drawing material toward their centers. Rotation works against that tendency. As Haumea turns, material near its equatorial regions experiences a strong outward effect associated with its rapid spin. The result is a triaxial ellipsoid, a body with 3 unequal dimensions. Picture an egg stretched considerably farther. Measurements derived from stellar occultations when Haumea passes in front of a distant star, have refined that shape. Current estimates place its longest dimension near 1,300 miles. Another spans roughly 1,040 miles, while its shortest measures around 670 miles. Few large bodies in the solar system depart so dramatically from a sphere. Its environment is equally extreme. Haumea travels roughly 43 astronomical units from the Sun on average, completing one orbit in about 285 Earth years. Surface temperatures can approach negative 400 degrees Fahrenheit. Under those conditions, exposed water remains frozen into an exceptionally hard surface. Spectroscopy, which identifies materials by analyzing how they interact with light, shows abundant crystalline water ice across Haumea. Crystalline ice possesses an ordered molecular structure and can be altered by energetic radiation over long periods. Its presence, therefore, raises questions about resurfacing processes that may refresh portions of the exterior. The dwarf planet is also unusually dense compared with many similarly sized objects beyond Neptune. Its density suggests a large, rocky fraction beneath a comparatively thin, icy exterior. If you could examine Haumea internally, you would likely find a body carrying proportionally more rock than many neighboring worlds. That combination gives us a physical record written into shape, spin, density, and surface composition. Rapid rotation alone cannot reveal every detail of Haumea's history, yet its present condition strongly suggests that its evolution involved a major disruptive event. Models of its formation commonly invoke an ancient collision capable of altering its angular momentum, the measure of rotational motion, while removing substantial icy material. You do not need to see that collision directly. Haumea still carries its consequences every 3 hours and 55 minutes. Each rotation preserves the motion of an event billions of years old, expressed through a world stretched almost to the limit that gravity can hold together. A collision can disappear while leaving its pieces behind. Around Haumea, astronomers have identified those pieces across an enormous region, reconstructing an ancient impact from objects that still share its distinctive chemical signature. Two fragments remained gravitationally bound as moons. The larger, Hi'iaka, measures roughly 190 miles across. Namaka spans about 105 miles. Their names come from daughters of Haumea, the Hawaiian goddess of childbirth and fertility. Hi'iaka travels farther from the dwarf planet, while smaller Namaka follows a closer orbit. Their motions are complicated. The moons gravitationally disturb one another, producing orbital variations that help researchers estimate masses and reconstruct their history. Those interactions also provide evidence that Haumea's system evolved substantially after the event that reshaped its parent body. Other fragments escaped farther. Astronomers have identified several Kuiper Belt objects whose orbital characteristics and unusually strong water ice signatures resemble Haumea. Together, they form the Haumea collisional family, one of the clearest known families produced by a major collision beyond Neptune. Finding relatives at such distances requires careful comparison. Researchers measure reflected sunlight, searching for absorption patterns produced by particular surface materials. They also calculate orbital paths backward and examine whether those trajectories could share a common origin. In Haumea's family, the combination of composition and dynamics points toward fragments stripped from the same ancestral body. The system gained another dimension in January 2017 when Haumea passed directly in front of a distant star from Earth's perspective. This event, called a stellar occultation, allows astronomers to measure an object by precisely timing how it blocks background starlight. Observatories across Europe watched the event. Haumea covered the star as expected, yet the instruments recorded additional brief drops in brightness before and after the main occultation. Something else was blocking the light. Analysis revealed a ring surrounding Haumea. The discovery, announced in October 2017, made it the first known object beyond Neptune with a confirmed ring. The ring circles roughly 1,420 miles from Haumea's center and spans about 43 miles in width. You cannot see this structure in a conventional photograph. Haumea is simply too distant and too small in our sky for existing telescopes to resolve the ring directly. Its presence was inferred from precisely timed interruptions of starlight, measured while the entire system lay billions of miles away. Later discoveries showed that Haumea is not unique among distant small worlds in possessing rings, expanding another category once associated mainly with giant planets. Yet its system remains exceptional in combination. No spacecraft has examined any of it nearby. We know the moons through their orbital motions, the family through shared ice and trajectories, and the ring through a distant star briefly disappearing behind material. No camera has directly resolved. An impact from deep solar system history remains readable through every fragment still moving around Haumea today. Makemake first entered human records as a few faint points captured on different nights. Mike Brown, Chad Trujillo, and David Rabinowitz identified the moving object in images taken at Palomar Observatory on March 31st, 2005. Because Easter had recently passed, the team used the informal discovery nickname Easter Bunny. Its permanent name reached much farther across human history. Makemake, pronounced Ma-Ke. Ma-Ke is the creator deity of the Rapa Nui people of Easter Island. The name suited a body found during the Easter season, while giving this distant world an identity drawn from Polynesian tradition. Makemake is roughly 890 miles across. It travels around the Sun once every 305 Earth years, following an orbit averaging about 46 astronomical units from our star. Surface temperatures hover near -400 degrees Fahrenheit, yet Makemake reflects considerable sunlight. From Earth, it ranks among the brightest known Kuiper Belt objects, surpassed there only by Pluto. Spectroscopy reveals why its surface is scientifically distinctive. Frozen methane dominates much of the exterior, accompanied by ethane and other products created as radiation alters methane over immense spans of time. Those compounds help produce Makemake's reddish coloring. They also indicate a surface capable of changing as volatile ices respond to its long journey around the Sunday. One major question concerned an atmosphere. In April 2011, Makemake passed across a distant star. Astronomers watched the stellar occultation from several observatories. If a substantial global atmosphere surrounded Makemake, the star should have faded gradually as its light passed through gas before reaching the solid surface. Instead, the disappearance was abrupt. So was the return. The observation placed strong limits on any global atmosphere present at that time. A localized atmosphere remains possible, particularly where sunlight warms volatile surface deposits, but Makemake lacked the extensive gaseous envelope researchers had considered plausible. Another mystery lasted longer. Repeated observations showed no companion around the dwarf planet. Then Hubble Space Telescope images, taken in April 2015, revealed a faint object nearby. The discovery was announced the following year. Its formal designation is Satellite of 2015, 1 of Makemake. Astronomers commonly call it Makemake 2. Estimates suggest the moon is roughly 100 miles wide, assuming a very dark surface. Its darkness helps explain why earlier searches missed it beside the much brighter dwarf planet. You can see how one unresolved companion changes the calculation. A well-measured satellite orbit would allow Makemake's mass and density to be determined through their mutual gravitational motion. Existing observations, however, have not yet constrained that orbit precisely enough to provide the definitive measurement astronomers want. No spacecraft has visited Makemake. Every detail we possess comes from light gathered across billions of miles, sometimes from Makemake itself, sometimes from a background star disappearing behind it. Even one of the brightest worlds beyond Neptune can still keep fundamental properties beyond our reach. New Horizons still carried usable fuel after passing Pluto in July 2015. Its primary mission had succeeded, but the spacecraft was already moving deeper into territory no probe had explored closely. Reaching another object required finding one almost directly along its existing path. That search began before the Pluto encounter. The Hubble Space Telescope examined a narrow region ahead of New Horizons, looking for something small enough to be primordial and positioned within the spacecraft's limited steering capability. Images taken on June 26, 2014, contained the target. At first, it was barely distinguishable from background light. The object received the designation 2014 MU-69. Mission teams later used the nickname Ultima Thule, an old expression for a place beyond the known frontier. In 2019, its official name became Arrokoth, a Powhatan word meaning sky, chosen with the involvement of Powhatan elders in the Tidewater region of Virginia. On January 1, 2019, New Horizons reached it. The spacecraft passed within roughly 2,200 miles, conducting the most distant, close exploration of a solar system object ever attempted. Radio signals carrying the observations required more than 6 hours to reach Earth. What appeared on those images looked unlike any world previously visited. Arrokoth is a contact binary, meaning two distinct bodies became joined together. One broad, flattened lobe connects through a narrow neck to a smaller companion. The larger component spans roughly 12 miles, while the smaller measures about 9 miles across. Their relationship mattered more than their unusual outline. Both lobes display remarkably similar coloring and surface composition. Their orientations also fit a low-energy merger far better than a violent collision. Researchers concluded that the components, formed near one another from the same local material, became gravitationally associated and gradually drew together. Their final meeting happened gently. Models indicate collision speeds of only a few miles per hour, slow enough for both bodies to remain largely intact. Instead of shattering, they settled together and preserved the geometry of their separate beginnings. You are looking at structure inherited from planetary infancy. Arrokoth's heavily preserved surface and primitive composition indicate that it has experienced remarkably little geological modification during roughly 4.5 billion years. Its environment protected it from the intense heating and frequent destructive collisions that transformed material closer to the sunday. 3 research papers published in Science in 2020 used New Horizons data to reconstruct this history. Their results supported formation through local collapse and gentle assembly rather than repeated high-speed impacts. That matters because objects like Arrokoth are surviving planetesimals, small building blocks from the era when planets were assembling. Its 2 joined lobes preserve a physical record of that process. We did not recover that record from a meteorite or infer it entirely through equations. A spacecraft crossed billions of miles and photographed the original architecture still intact. Planet formation once looked much more violent in many computer models. Small objects moved through the young solar system, collided repeatedly, fragmented, and accumulated again. Given enough impacts, increasingly large planetesimals could emerge, providing the raw bodies from which planets eventually grew. Arrokoth forced scientists to examine another pathway. Its paired structure preserved details that destructive collisions should have erased. The two components share closely matched colors and compositions, while their flattened shapes and alignment indicate formation within the same local environment. Their final joining occurred with too little energy to resemble the repeated high-speed collisions expected in older models. Three research teams analyzing New Horizons observations reached a similar conclusion in papers published in Science during 2020. Arrokoth's components probably formed near each other inside the protoplanetary disk, the broad rotating mixture of gas, dust, and ice surrounding the young Sunday. The key process begins with tiny particles. Pebble accretion describes growth through the collection of small solid particles, often ranging from grains to pebble-sized material. Gas in the young disk influenced their motion, allowing concentrations of solids to develop. Under suitable conditions, a dense cloud of these particles could become massive enough for its own gravity to take control. Then local gravitational collapse begins. Instead of requiring countless destructive impacts, the concentrated material contracts under mutual gravity. Within that collapsing region, separate clumps can form together and emerge already gravitationally connected. Arrokoth appears to preserve such an arrangement. Its lobes may have begun as two neighboring bodies orbiting a shared center of mass. Gas drag and interactions with surrounding material gradually removed orbital energy. Their separation decreased over time until contact became inevitable. Because both objects originated within the same local reservoir, their chemical similarities follow naturally. That changes what we can infer from a body only about 22 miles long. If this mechanism operated widely throughout the Kuiper Belt, many primordial planetesimals may have assembled through local collapse rather than prolonged sequences of destructive collisions. You can extend that possibility toward the young inner solar system. Conditions nearer the Sun differed substantially, especially in temperature and available ices. Yet the underlying physics of particle concentration, gravitational collapse, and pebble accretion could also have contributed to the planetesimals that eventually supplied material to Earth and the other rocky planets. Arrokoth, therefore, offers more than a preserved example. It gives planetary scientists a physical constraint for testing simulations of the solar system's earliest stages. Any successful formation model must produce structures compatible with what New Horizons actually observed. Its survival also carries an important limitation. Arrokoth preserves formation exceptionally well because later disruptions spared it. Much of the surrounding population experienced a different history. The present Kuiper Belt is thinner, dynamically excited, and extensively rearranged compared with its original state. Arrokoth records how small worlds could begin, while the altered orbits around it record how dramatically their neighborhood later changed. The planets themselves once wandered. During the solar system's youth, Jupiter, Saturn, Uranus, and Neptune occupied a more compact arrangement than the one we observe today. Their gravity interacted with a vast disk of leftover planetesimals, small bodies surrounding the young planetary system. Every encounter exchanged momentum. A planetesimal could be scattered inward, while a planet shifted slightly outward, or the reverse. Multiplied across enormous populations and millions of years, these tiny exchanges changed planetary orbits. Neptune moved outward dramatically. As its orbit expanded, Neptune disturbed the ancient population beyond it. Some objects were captured into orbital resonances, repeating gravitational relationships in which their periods became synchronized with Neptune's. Others acquired more elongated or tilted paths. Many were scattered toward distant regions, inward toward the giant planets, or completely beyond the sun's gravitational control. The modern Kuiper Belt is partly the surviving record of that restructuring. One influential explanation is the Nice model, named for Nice, France, where researchers developed its original form during the early 2000s. In those simulations, the giant planets began closer together, while an enormous planetesimal disk extended beyond them. Their gradual migration eventually destabilized the original configuration. Jupiter and Saturn played central roles. Changes in their orbital relationship amplified gravitational disturbances throughout the outer solar system. Uranus and Neptune could shift substantially, while countless smaller bodies were redistributed. Early versions of the Nice model connected this instability with an intense episode of impacts around 3.9 billion years ago, traditionally called the Late Heavy Bombardment. Lunar craters preserve evidence of major ancient impacts, although modern research debates whether there was one sharp bombardment spike or a more extended decline in impact rates. Either way, the early solar system was dynamically active. Models suggest the primordial planetesimal disk beyond the giant planets contained many Earth masses of material. The present Kuiper Belt contains only a small fraction of one Earth mass. Much of the original population was removed as the giant planets rearranged their surroundings. You can still read aspects of that history through orbital structure. Resonant populations reveal Neptune's gravitational influence. Scattered objects preserve highly eccentric trajectories. Other bodies occupy inclinations difficult to produce in a simple, undisturbed disk. Haumea's own unusual path exists within this reshaped architecture, even though its collision added another layer to its history. Closer to the Sun, Jupiter also influenced what became the asteroid belt. Its strong gravity stirred orbital velocities and disrupted efficient planetary growth there. Ceres, therefore, belongs to material that survived in a region where assembling another major planet became difficult. But migration cannot explain every distant orbit we observe. Some objects remain too detached from Neptune for ordinary scattering by the known planets to account easily for their present paths. Their trajectories preserve information from conditions we have not completely reconstructed. The small worlds are therefore more than survivors. Their orbits function like dynamical records, preserving gravitational events after the planets responsible have moved elsewhere. Sedna spends most of its existence where the familiar architecture of the solar system has almost disappeared. From there, even Neptune belongs to the inner reaches. The sun remains its gravitational anchor, yet its light has weakened enormously. Astronomers Mike Brown, Chad Trujillo, and David Rabinowitz discovered Sedna on November 14, 2003. Images taken at Palomar Observatory revealed a faint object moving against distant background stars. Continued observations soon exposed an orbit unlike anything previously known. Sedna is roughly 620 miles across. Its surface temperature falls near 400 degrees below 0 Fahrenheit. Observations show an unusually reddish surface, placing Sedna among the reddest known bodies in the solar system. That coloring may come from tholins, complex organic substances created when radiation alters simpler carbon-bearing compounds over immense periods. Similar materials appear elsewhere in the outer solar system. On Sedna, billions of years of exposure may have transformed much of the visible surface. Its orbit presents the deeper puzzle. At perihelion, meaning its closest point to the Sun, Sedna remains roughly 76 astronomical units away. Neptune averages only about 30 astronomical units from the Sunday. Sedna, therefore, never approaches Neptune closely enough for ordinary encounters with that planet to explain its detached orbit. Then Sedna travels outward. Its estimated aphelion, the most distant point of its orbit, lies around 937 astronomical units from the Sunday. Completing that immense circuit requires roughly 11,400 Earth years. Human civilization has recorded only a tiny fraction of one Sednan year. Think about what that means. As we follow its path, Sedna was approaching the Sun throughout essentially all of written human history, yet nobody knew it existed until 2023 years after the beginning of the Common Era. The orbital geometry matters more than the distance itself. Neptune can scatter smaller objects into elongated paths, creating populations whose trajectories still carry evidence of planetary encounters. Sedna is different. Its perihelion remains too distant for Neptune to have produced its present orbit through conventional scattering under the solar system's current arrangement. Something else appears to have raised that orbit. Several explanations remain scientifically plausible. During the Sun's infancy, another star passing through its birth cluster may have gravitationally disturbed Sedna. The combined gravity of nearby young stars could also have reshaped distant objects before the Sun escaped its stellar nursery. Another possibility involves an unseen massive planet orbiting far beyond Neptune. No explanation has been confirmed. Sedna therefore occupies a region sometimes called the inner Oort cloud, although its exact classification remains debated. It marks a population detached from direct control by the known giant planets. And Sedna no longer stands alone. Other distant objects with unusually large perihelia have since appeared in astronomical surveys. Their existence transformed Sedna from one orbital anomaly into evidence that the farthest solar system contains a structure we still cannot fully account for. A pattern can become more interesting when a new discovery refuses to fit it. Sedna had already shown astronomers that distant detached orbits existed. Then other bodies appeared, allowing researchers to ask whether those paths preserved a shared history rather than isolated accidents. The second widely recognized sednoid was discovered in 2012 by astronomers Scott Shepard and Chad Trujillo. Its formal designation is 2012 VP113. The discovery team informally called it Biden, a playful reference to the number 10013. Its closest approach lies beyond 80 astronomical units. Neptune cannot readily sculpt an orbit that detached. Another member followed. Lelikuhonua, discovered during observations begun in 2015 and announced in 2018, travels on an even more extended path. Its Hawaiian name describes a celestial body reaching toward the heavens. With 3 sednoids known, astronomers noticed something provocative. Their orbital orientations appeared clustered rather than randomly scattered. One useful quantity is longitude of perihelion, which describes the direction in space where an orbit points toward its closest solar approach. Sedna, 2012 VP 113, and Lelikuhonua occupied a comparatively similar range. Could an unseen gravitational influence maintain that arrangement? The sample was tiny, so each discovery mattered enormously. In July 2025, researchers using the Subaru telescope announced a fourth sednoid. Its designation is 2023 KQ14, and the team nicknamed it Ammonite. Ammonite approaches within roughly 66 astronomical units of the Sunday. Numerical simulations indicate its orbit has remained remarkably stable for about 4.5 billion years. Its trajectory, therefore, preserves conditions near the solar system's beginning. But Ammonite complicated the apparent pattern. Its present orbital orientation does not cluster with the other three. Instead, it points in a substantially different direction. Simulations suggest all four may have possessed more similar orbital orientations roughly 4.2 billion years ago, before gradual gravitational precession altered them. Precession is the slow rotation of an orbit's orientation over immense spans of time. That changes what the sednoids can tell us. Their unusual distances still demand an explanation because the known planets cannot easily create such detached paths under present conditions. Yet their current arrangement no longer offers a simple four-object alignment. Possible causes reach deep into solar history. A passing star could have disturbed the young outer regions. A rogue planet might once have crossed these distances before being expelled. Galactic tides could also contribute. A massive undiscovered planet remains another hypothesis, although Ammonite places new constraints on where such a body could travel. When we look at these four objects together, we are reading orbital archaeology. Their paths preserve gravitational events older than Earth's present surface, while their differences prevent an easy answer. Whatever shaped this remote population left evidence in motion encoded across journeys lasting thousands of years. Gravity can reveal a world before anyone sees its surface. Astronomers have found planets around distant stars through exactly that principle, measuring what unseen mass does to visible objects. In the far solar system, researchers have wondered whether the same method is pointing towards something enormous. In 2016, astronomers Konstantin Batygin and Mike Brown proposed Planet 9. Their calculations suggested a massive planet could explain peculiar orbital patterns among distant trans-Neptunian objects, bodies traveling beyond Neptune. The proposed world would possess several times Earth's mass and follow a long, eccentric orbit hundreds of astronomical units from the Sunday. At those distances, sunlight becomes extremely weak. A planet reflecting that light could appear as an exceptionally faint point among countless background stars. Its movement across the sky would also be slow, making identification difficult across observations separated by limited periods. The hypothesis depends on gravity. A sufficiently massive distant planet would gradually reshape smaller orbits through repeated gravitational interactions. Over immense periods, those subtle tugs could organize certain trans-Neptunian objects into patterns resembling those already observed. In some models, Planet 9 may itself be a survivor of the solar system's turbulent youth, displaced outward during interactions among the growing giant planets. Batygin and Brown continued refining the idea. In 2024, they analyzed 17 distant objects whose trajectories are difficult to reproduce using the known planets alone. Their simulations strengthened the case that an additional gravitational influence could be operating beyond Neptune. But Ammonite introduced an important complication. The sednoid announced in 2025 follows an orientation different from the pattern that originally motivated Planet 9. Some simulations indicate that particular versions of the proposed planet's orbit struggle to preserve ammonite over billions of years. That does not automatically eliminate every possible Planet 9 configuration, but it narrows the available possibilities. Another explanation reaches into the past. Astronomer Yukun Huang and colleagues have explored whether an additional planet once occupied the distant solar system before eventually being ejected. Such a vanished world could have altered remote objects during the solar system's earliest stages, leaving orbital structures after the planet itself disappeared. Observational bias remains another concern. Telescopes have surveyed some regions more thoroughly than others. Distant objects are easiest to discover near particular portions of their elongated orbits, meaning an apparent celestial pattern can emerge from where astronomers happen to search. Now the search is gaining a much wider view. The Vera C. Rubin Observatory in Chile carries a camera containing 3.2 billion pixels behind an approximately 28-foot primary mirror. Its repeated survey of the southern sky is designed to detect changing and moving objects with extraordinary depth. For Planet 9, that coverage matters. A discovery would add another major world to the solar system. Continued absence would progressively restrict where such a planet could hide. Either result turns an invisible gravitational hypothesis into something astronomy can test against the sky itself. From Earth, many of the solar system's largest undiscovered worlds would barely look like worlds at all. They arrive in telescope images as points of light, often occupying only a few pixels across repeated observations. Yet some are large enough for their own gravity to reshape them. That creates an unusual census problem. The International Astronomical Union formally recognizes 5 dwarf planets, while many additional bodies satisfy much of the physical case. Astronomer Mike Brown maintains a frequently updated assessment of these candidates. His current ranking places dozens in categories ranging from nearly certain to highly likely or likely dwarf planets. Gonggong ranks among the strongest examples. Roughly 800 miles across, it carries the name of a destructive water deity from Chinese mythology. Its small moon, Xiangliu, follows alongside. Gonggong travels on a strongly inclined orbit, tilted about 30 degrees from the solar system's main plane, suggesting a complicated dynamical history. Quaoar presents a different puzzle. At roughly 680 miles across, it possesses a moon named Weiwat and at least 2 rings. The first ring, announced in 2023, occupies a region beyond the classical Roche limit. That boundary describes where tidal forces normally prevent orbiting material from assembling into a moon. Beyond it, particles should more easily gather under their mutual gravity. Quaoar's outer ring remains dispersed instead. Collisions between unusually elastic particles and gravitational resonances with Quaoar's rotation may help maintain the structure, although its behavior continues testing conventional ring models. Then there is Orcus. Its orbit resembles Pluto's in several important ways, yet the 2 objects occupy opposing phases of their paths around the Sunday. This relationship earned Orcus the informal description of anti-Pluto. Its companion, Vanth, is unusually substantial relative to Orcus, making the pair valuable for measuring the system's mass and investigating its origin. Farther down the candidate lists sit Varuna, Salacia, and Varda. Each remains physically unresolved from Earth. Their sizes, densities, surfaces, and shapes must instead be reconstructed indirectly through thermal radiation, changing brightness, orbital dynamics, and stellar occultations. An occultation occurs when one of these bodies crosses a distant star. For a few moments, the star disappears. Precisely timed from multiple locations, that disappearance can trace the object's outline with surprising accuracy. This is why classification remains difficult. Determining whether gravity has pulled a distant body into equilibrium requires knowing its actual three-dimensional shape, something a single point of reflected sunlight cannot directly reveal. The Vera C. Rubin Observatory is already changing that inventory. Preliminary observations reported in 2026 produced hundreds of trans-Neptunian discoveries before its decade-long legacy survey of space and time had fully begun. As those observations accumulate, you can expect the outer solar system to become increasingly crowded. The familiar five dwarf planets represent only the confirmed portion of a population whose true scale is still emerging. An atmosphere does not always behave like a permanent shell. Around some small worlds, it may appear only when conditions permit, survive briefly, then collapse back onto the surface. Far from the sun, that cycle can unfold across generations. Ceres provided an early example. Using the Herschel Space Observatory, astronomers detected water vapor around the dwarf planet during observations in 2012 and 2013. The signal was extremely weak and variable, indicating localized releases rather than a stable atmosphere surrounding the entire world. Researchers estimated that Ceres was releasing roughly 13 pounds of water each second during active periods. Sunlight warming exposed surface ice could drive some of that activity through sublimation, the direct transition from solid ice into vapor. Later observations also raised the possibility that energetic particles from the sun help release water molecules from surface material. Either mechanism produces something temporary. Individual molecules escape, fall back, or become redistributed across the surface. Ceres, therefore, carries an exosphere, an extraordinarily thin envelope whose particles rarely collide with one another. Farther outward, the physics becomes even more delicate. Small bodies possess weak gravity, while temperatures keep volatile compounds frozen for long intervals. Yet methane, nitrogen, carbon monoxide, and other ices can become gases when sunlight warms suitable surface regions. A slight temperature change may therefore transform the environment above an entire landscape. Makemake demonstrates how difficult these atmospheres are to detect. During a stellar occultation in 2011, the dwarf planet crossed directly in front of a distant star. The starlight disappeared sharply instead of fading gradually through surrounding gas. That observation ruled out a substantial global atmosphere at the time. A patchy atmosphere remains possible. Sunlit deposits of nitrogen or methane could locally sublimate, creating temporary concentrations of gas too limited for that occultation to reveal. Makemake's elongated orbit also changes the solar energy reaching its surface, allowing atmospheric conditions to evolve during its roughly 305-year journey around the Sunday. Haumea offers the opposite case. No atmosphere has been detected there. Its surface remains dominated by crystalline water ice, while temperatures near 400 degrees below 0 Fahrenheit suppress substantial vapor production. Its low gravity also makes retaining escaping molecules difficult. When we compare these bodies, the familiar idea of atmosphere begins to loosen. On Earth, air surrounds us continuously. On distant, icy worlds, an atmosphere can behave more like a seasonal surface process. As an object approaches the sun, volatile ice may sublimate. Gas accumulates above the terrain. Moving outward again reduces the available heat, allowing molecules to condense and freeze back onto the ground. Some worlds may repeat this exchange across centuries. You could visit the same body at different points in its orbit and measure different environments. What appears airless during one astronomical era may carry vapor during another, making atmosphere itself a changing phase in the life of an icy world. A beam of sunlight can reveal a world's history without touching it. When reflected light is separated into its component wavelengths, certain colors weaken where surface molecules absorb them. These absorption patterns act like fingerprints. Through them, we can identify materials across billions of miles. Ceres carries the chemistry of a comparatively warm birthplace. Its surface contains hydrated minerals, compounds whose crystal structures include water or components derived from water. Salts and carbon-rich, organic material appear there as well. Ammonia-bearing minerals add another clue, suggesting either unusual formation conditions or material transported inward from colder regions. Beneath that surface, Ceres underwent partial differentiation. Internal heating allowed materials of different densities to separate, with rock concentrating deeper, while ice and water-rich compounds remained higher. Radioactive decay likely supplied part of this early heat. The chemistry therefore records geological processing inside a body only about 580 miles wide. Haumea preserves another kind of transformation. Spectroscopy shows abundant crystalline water ice across its exterior, yet its overall density indicates a body unusually rich in rock. That combination fits its ancient collision history. Much of an earlier icy mantle was stripped away, leaving a denser survivor with only a comparatively thin, frozen covering. You are effectively seeing an interior exposed by violence. Makemake retained a different inventory. Methane dominates important portions of its spectrum, accompanied by ethane and other irradiation products. At temperatures approaching 400 degrees below 0 Fahrenheit, these substances remain frozen across the surface. Solar ultraviolet radiation and energetic particles continually alter them, gradually producing more complex carbon-rich compounds. Arrokoth carries this chemistry farther into the primordial record. Both lobes share remarkably similar reddish coloration. Researchers associate that color with tholins, complex organic materials produced when simple carbon and nitrogen-bearing molecules receive prolonged radiation. Tholins are not one specific chemical substance. The term describes mixtures created through radiation-driven reactions under frigid conditions. Their distribution matters. Arrokoth's two lobes match closely in color and composition, supporting formation from material gathered within the same local environment. Their surfaces have spent roughly 4.5 billion years preserving chemistry inherited from the solar system's earliest disk. Across these bodies, distance helped determine what could survive. Nearer the young sun, higher temperatures favored rock, altered minerals, and water-related chemistry. Farther outward, colder environments preserved volatile substances such as methane, nitrogen, and carbon monoxide that could not remain frozen closer in. But location was only the beginning. Impacts removed layers. Internal heating rearranged materials. Radiation manufactured new compounds. Orbital evolution carried bodies away from their birthplaces. When we examine these frozen surfaces today, we are reading several histories at once. Composition records, birthplace, temperature, collisions, radiation, and geological change. Every absorption line in a spectrum preserves another piece of that record, written into material older than any surface remaining on Earth. Taken together, these worlds reveal something larger than individual discoveries. Their unusual features are connected by a common history. Each preserves evidence from processes that shaped the solar system, yet each preserves a different part. Ceres sits inside the asteroid belt, where early planetary growth was disrupted. For generations, it appeared geologically exhausted. We now know its interior preserved water, salts, and organic chemistry long after its formation. Beneath Akator crater, evidence points toward a deep reservoir of concentrated brine. A body once treated as inert instead carries traces of internal activity. Far beyond Neptune, Haumea records another history. Its rapid rotation stretches its figure into an extreme ellipsoid. Two moons accompany it. A ring circles the distorted body, while related fragments occupy neighboring regions of orbital space. Together, those fragments preserve the aftermath of an ancient collision on a scale we can reconstruct billions of years later. Makemake offers a subtler puzzle. For roughly a decade, astronomers measured its combined light without recognizing that a dark moon contributed to those observations. The companion, discovered with the Hubble Space Telescope in 2015, changed estimates of Makemake's physical properties. Even a world bright enough to rank among the most prominent Kuiper Belt objects could conceal an important part of itself. Then there is Arrokoth, its two flattened lobes joined at low speed, preserving a structure inherited from planetary construction itself. New Horizons encountered it on January 1st, 2019. The resulting images provided direct evidence that small bodies could assemble through gentle gravitational processes rather than repeated destructive impacts. A world only about 22 miles long altered theories describing how much larger worlds began. The sednoids carry their information differently. Their extreme orbits extend into regions where Neptune cannot readily account for their present paths. Sedna provided the first clear example. Additional discoveries transformed one peculiar orbit into a population demanding explanation. Whether their arrangement reflects an undiscovered planet, an ancient stellar encounter, observational bias, or another mechanism remains unsettled. What does strangeness mean when exceptions keep accumulating? Here, it means our categories were built from incomplete observations. 225 years ago, none of these bodies belonged to human knowledge. 30 years ago, most remained undetected. Even today, many comparable objects probably exist beyond the reach of present surveys. You can think of these small worlds as surviving records rather than peripheral debris. Their chemistry preserves ancient temperatures. Their shapes preserve collisions and mergers. Their orbits retain gravitational disturbances whose causes may have vanished. Rings expose gaps in current models, while hidden moons change measurements from afar. We began by calling such bodies minor. Their physical dimensions justified the word. Their scientific importance does not. Across the solar system, the smallest recognized worlds preserve evidence that the larger planets have erased, buried, melted, or transformed. For the first time, our catalogs are growing faster than our spacecraft can follow. Telescopes are revealing distant worlds by the thousands, while physical exploration remains concentrated around only a few. The imbalance is becoming part of the science itself. Dawn remains the only spacecraft ever to visit Ceres. After completing its final observations, the mission exhausted its hydrazine fuel in October 2018. Controllers could no longer orient the spacecraft reliably toward Earth. Dawn remains in orbit around Ceres, carrying instruments that transformed a point of light into a mapped geological world. No comparable mission is traveling toward Haumea or Makemake. None is headed toward Gong, Quaoar, Orcus, or the other strong dwarf planet candidates. For these objects, we still depend on photons crossing enormous distances before entering telescopes near Earth. Sedna presents an even greater challenge. Its extraordinary orbit carries it toward perihelion, the closest point to the Sun, around 2076. That approach creates a rare opportunity because Sedna will remain more accessible than during most of its roughly 11,400-year journey. Mission studies published in 2021 examined possible trajectories using gravitational assists from planets such as Jupiter. Favorable launch opportunities occur around the late 2020s and early 2030s. Depending on the trajectory, a spacecraft could reach Sedna decades later. The timing matters. Miss the useful geometry, and reaching Sedna becomes considerably harder. Yet no dedicated Sedna mission has entered funded development. Meanwhile, discovery is accelerating closer to home. The Vera C. Rubin Observatory uses an enormous digital camera to repeatedly photograph the southern sky. Its long survey is expected to reveal vast numbers of previously unknown outer solar system bodies. Some will become dwarf planet candidates. Others may occupy orbital families we have never recognized. That means you could watch the known architecture of our planetary system change within a human lifetime. Ceres offers a different opportunity. It is vastly easier to reach than Sedna, and Dawn already provided detailed maps for selecting scientifically valuable destinations. A future lander could examine surface salts directly. More ambitious hardware could collect material from deposits associated with ancient brines, allowing laboratory instruments to measure chemistry impossible to resolve from orbit. Such a mission remains a proposal rather than a spacecraft under construction. This creates an unusual moment for planetary science. We possess enough evidence to identify important questions, yet lack missions capable of answering many of them directly. Remote observations can measure color, orbit, rotation, and sometimes composition. They cannot replace a sample, a drill, or instruments resting on alien ground. Our maps will therefore expand before our footprints do. New objects will receive names. Strange orbital patterns will sharpen. Candidate worlds will multiply across databases. For now, the frontier is advancing through observation faster than exploration can physically reach it. The worlds are already there. What changes next depends partly on which ones humanity decides are worth visiting. Long before telescopes could identify these worlds, human cultures were already naming forces larger than themselves. Harvest, creation, birth, sea, and sky became figures carried through generations. Centuries later, astronomers borrowed those names for objects whose histories reach far deeper into time. Ceres received hers first. Giuseppe Piazzi discovered the body on January 1st, 1801, and named it for the Roman goddess associated with agriculture and grain. The choice also honored Sicily, where Piazzi worked, because Ceres held particular importance in the island's ancient traditions. A familiar earthly name entered astronomy beside an unfamiliar class of object. More than 2 centuries later, Haumea joined the map. Its name comes from Hawaiian tradition, where Haumea is associated with fertility and childbirth. The astronomical connection became unusually fitting. The dwarf planet is accompanied by moons and a recognizable family of fragments sharing related surface properties, remnants linked to the same ancient body. Its moons deepen that connection. Haiyaka and Namaka bear names associated with daughters of Haumea in Hawaiian tradition. Here, mythology became a vocabulary for describing an astronomical family whose relationships are measurable through orbital dynamics and chemistry. Makemake draws from another Pacific tradition. Its name honors the creator deity central to the culture of Rapa Nui, the indigenous people of Easter Island. Astronomer Michael Brown and his colleagues had temporarily called the object Easter Bunny because its discovery occurred shortly after Easter in 2005. The eventual name preserved that association through a deeper cultural reference. Arrokoth followed a different path. Before its New Horizons encounter, The object carried a provisional nickname that was later retired. In 2019, the mission team announced Arrokoth, a word meaning sky in the Powhatan and Algonquian languages. The naming involved consultation with Powhatan representatives from the region where the object had been discovered using the Hubble Space Telescope. Then we reach Sedna. Michael Brown's team selected a name from Inuit tradition for a body found at an extraordinary distance. Sedna is a powerful figure associated with the sea and marine animals dwelling in the depths beneath the human world. Astronomers saw a geographical metaphor in that mythology. Their newly discovered object inhabited an astronomical depth beyond the familiar planetary region. These names do more than replace catalog designations. They give language to places no human being has visited and, in most cases, no spacecraft has approached. Yet their meanings also remind us where the naming happens. Every title originates here, among cultures formed on one small planet. We project words from islands, oceans, harvests, families, and skies onto bodies separated from us by billions of miles. The worlds themselves are ancient, their names are human. And at the edge of our map, those two histories now travel together. A boundary, once drawn around the sun's warmth, has become harder to defend. Liquid water does not need a bright surface or a temperate sky. On small worlds, heat can come from within, surviving beneath ice long after sunlight becomes too weak to matter. Ceres gives us one of the clearest examples. Its brines, mixtures of water and dissolved salts, can remain liquid at temperatures where pure water freezes. Beneath Arrokoth crater, evidence gathered by the Dawn spacecraft points to reservoirs connected with relatively recent geological activity. Radioactive elements inside the rocky interior provide another source of energy. As unstable atoms decay, they release heat over immense spans of time. That mechanism changes the geography of habitability. Distance from the sun still matters, especially at the surface. Yet beneath insulating layers of ice and rock, entirely different conditions can persist. We see a stronger version around Saturn. Enceladus measures only about 310 miles across, yet beneath its icy shell lies a global ocean. The Cassini spacecraft repeatedly passed through material erupting from fractures near the South Pole. Its instruments detected water vapor, salts, organic compounds, and molecular hydrogen. That hydrogen matters. On Earth, microbes living around hydrothermal systems can use hydrogen as an energy source. Cassini found no organisms, and its measurements were never designed to prove biology. Still, the chemistry showed that water and rock interact inside Enceladus, creating conditions relevant to life. Europa expands the same idea around Jupiter. Evidence from the Galileo spacecraft showed that an electrically conductive layer exists beneath its surface, consistent with a salty ocean. Geological patterns across the ice also suggest movement between the surface and deeper layers. If you could descend through that frozen exterior, sunlight would disappear long before the potentially habitable environment began. Ceres is different from both moons. Its remaining liquid appears more limited, and its internal history followed another path. Yet, organic molecules have been identified on its surface, while carbonate salts preserve evidence of water-driven chemistry. Together, these findings broaden what we mean when discussing a potentially habitable environment. Habitability is not evidence of inhabitants. No confirmed organism, fossil, or biological signal has been discovered beyond Earth. The distinction matters. But our search criteria have changed. 30 years ago, attention centered heavily on places where sunlight might keep surface water liquid. Now we also examine buried oceans, brine pockets, radioactive heating, chemical gradients, and interactions between water and rock. A small frozen body can therefore remain chemically active beneath an ancient exterior. It may preserve water for extraordinary periods. It may contain carbon chemistry and usable energy together. Across the solar system, the possible homes for those ingredients have multiplied. Life remains unconfirmed. The environments worth searching no longer resemble Earth's surface. A planet is a poor place to store an untouched memory. Its own activity keeps rewriting the evidence. Crust melts, atmospheres escape, volcanoes bury landscapes, and impacts rearrange what survives. After billions of years, the original material may remain, yet its earliest arrangement has largely disappeared. Earth demonstrates this constantly. Plate tectonics carries old crust into the mantle, while new crust forms elsewhere. Almost no surface from Earth's first billion years remains intact. Venus followed another path, with widespread volcanism obscuring much of its ancient record. Mars preserved more, although lava flows, erosion, and repeated impacts altered enormous regions. Even the Moon accumulated overlapping scars. Small worlds can preserve a different history. Arrokoth offers perhaps the purest example we have examined directly. For roughly 4.5 billion years, its material has avoided the extensive melting and geological recycling familiar on planets. The chemistry of its surface still reflects substances inherited from the region where it formed. Its joined lobes preserve physical evidence of how small bodies assembled during the solar system's infancy. You can think of that preservation as information stored in matter. Shape records motion, minerals record water, ice records temperature, organic compounds record radiation and chemistry across immense spans of time. Ceres preserves another kind of evidence. Hydrated minerals contain water within their mineral structure and reveal ancient interactions between rock and liquid. Carbonates and salts provide further traces of chemical environments that existed deep in its history. Larger rocky planets formed from related primordial materials, but their interiors became hot enough to transform much of that early evidence. Farther outward, preservation becomes even more extreme. Methane frost on Makemake survives where stronger solar heating would remove it. Haumea's crystalline water ice carries information about resurfacing and its unusual collisional history. Sedna and Arrokoth retain complex organic material produced as simpler carbon-bearing compounds endured prolonged radiation. Cold helps maintain the record. At temperatures far below those found across most planetary surfaces, many chemical reactions proceed extremely slowly. Geological activity can also become limited. Material that would be transformed, buried, vaporized, or recycled elsewhere may remain recognizable for billions of years. This is why tiny worlds matter beyond their size. When we study their spectra, densities, minerals, surfaces, and orbital families, we are examining surviving pieces of the material available during planet formation. The major planets show what gravity, heat, differentiation, atmosphere, and time eventually created. Smaller bodies preserve more of the starting conditions. Together, those records let us reconstruct a history no single world contains. The solar system's largest members reveal its evolution, while some of its smallest members still carry fragments of its original state. Neptune's orbit once seemed like a reasonable boundary for imagining the solar system. Today, it marks something closer to the beginning of an enormous unexplored volume. At roughly 30 astronomical units from the Sun, Neptune circles inside a system whose gravitational population may extend thousands of times farther. The familiar Kuiper Belt occupies only the first portion. Its main concentration reaches roughly 50 astronomical units, while scattered objects travel much farther on elongated paths. Sedna can retreat to roughly 936 astronomical units. Even there, we may still be near the inner reaches of what belongs to the Sunday. Beyond lies the proposed Oort cloud, a vast reservoir inferred rather than directly photographed. Its inner regions may begin around 2,000 astronomical units away. The outer boundary could approach 100,000 astronomical units, where the Sun's gravitational influence competes increasingly with passing stars and the Milky Way. No telescope has resolved this cloud as a structure. Instead, we detect occasional messengers. Long-period comets arrive from immense distances on trajectories suggesting a roughly spherical reservoir surrounding the planetary system. Some require tens of thousands, hundreds of thousands, or even millions of years to complete their journeys around the Sunday. Their existence provides indirect evidence for an enormous hidden population. Estimates suggest the Oort cloud could contain hundreds of billions or perhaps trillions of icy bodies. Most would be small. Yet, planetary formation models allow the possibility that considerably larger objects were scattered outward alongside them. How many could be round worlds? We do not know. At those distances, reflected sunlight becomes extraordinarily faint. Brightness decreases rapidly as an object moves outward, making even substantial bodies difficult to distinguish against background stars. Their apparent movement also becomes extremely slow. Detecting one may require observations separated by long intervals before its motion becomes measurable. This leaves an unusual imbalance in our knowledge. Every major planet occupies the innermost fraction of the Sun's enormous gravitational domain. Nearly every asteroid and confirmed dwarf planet does too. The region we have cataloged most successfully represents only a small portion of the available territory. The rest is reconstructed through gravity, comet trajectories, numerical simulations, and scattered detections. Somewhere within those distances, an undiscovered planet could remain faint enough to escape existing surveys. Smaller dwarf planets could be vastly more numerous. Ancient bodies expelled during planetary migration may still preserve compositions from regions that no longer exist in their original form. There may also be objects captured from other stars during the Sun's youth, when it likely formed among neighboring stars in a stellar nursery. Such bodies would carry material born around another sun. So when you picture the solar system, the 8 planets occupy only its familiar center. Beyond them stretches a domain measured in tens of thousands of astronomical units, populated largely through inference. We have mapped the neighborhood around our star. Most of its distant territory has never been seen directly. Discovery often begins with an absence nobody recognizes as an absence. A region seems empty, a measurement seems complete, an object seems understood. Then an observation arrives from the right instrument, at the right angle, and the map acquires something that had been there all along. Ceres demonstrates how long that can take. Giuseppe Piazzi discovered it on January 1st, 1801. For more than 2 centuries, astronomers watched its reflected light and refined its orbit. Yet its brines, salts, and complex geology remained inaccessible until Dawn entered orbit in 2015. Familiarity had concealed complexity. The outer solar system produced an even larger correction. Astronomers had proposed populations beyond Neptune, but no member of what we now call the Kuiper Belt was confirmed until 1992. David Jewett and Jane Liu found the object designated 1992 QB1 after years of systematic searching. One faint point established that the distant region was populated. Other discoveries required different kinds of luck. Haumea's ring appeared during a stellar occultation in 2017. An occultation occurs when a nearby body crosses a distant star, briefly blocking its light. Observatories measured extra dips before and after Haumea itself passed across the star. Those brief interruptions revealed material circling the dwarf planet. Makemake concealed another companion. Its moon remained unresolved through years of observations until the Hubble Space Telescope detected it in 2016. The discovery helped explain puzzling thermal measurements previously attributed entirely to Makemake. A second body had been contributing information without announcing itself. Arrokoth entered our catalog through necessity. After New Horizons passed Pluto, mission planners searched for another reachable object. The Hubble Space Telescope examined a narrow region along the spacecraft's possible trajectory and found a suitable target. Humanity eventually flew past a primordial body because engineers needed somewhere attainable to send a spacecraft already moving outward. Sedna emerged from a broader survey, yet its discovery exposed how strongly observation shapes knowledge. Distant objects spend much of their enormous orbits too faint for existing searches. Surveys cover limited areas, operate for limited durations, and favor objects bright enough to register against crowded stellar backgrounds. You can only discover what your method allows you to notice. That limitation has followed astronomy from photographic plates to modern digital surveys. Improved sensitivity reveals fainter objects. Wider coverage exposes populations missed by narrow searches. Longer observing campaigns detect motion too gradual to recognize quickly. The pattern is less about hidden worlds deliberately evading us than about incomplete sampling. Our instruments define the boundaries of the detectable solar system at any given moment. Each expansion of those boundaries has changed the inventory. Ceres gained an active interior. The Kuiper Belt gained thousands of members. Dwarf planets gained rings and moons. Extreme orbits gained companions. What once appeared empty repeatedly became populated when our observations improved. Planetary classification can sound like a judgment about importance. Scientifically, it serves a narrower purpose. Under the definition adopted by the International Astronomical Union in 2006, one distinction separates a planet from a dwarf planet: gravitational control of the region surrounding its orbit. Both categories orbit the Sunday. Both require enough self-gravity to become approximately round. But a planet must also clear its orbital neighborhood, meaning it has become gravitationally dominant among comparable bodies sharing that zone. Size alone cannot decide the label. Ceres illustrates why. At roughly 584 miles across, it contains differentiated layers, meaning its interior separated according to density during its early history. Water altered its minerals. Brine survived beneath its crust. Organic compounds occur on its surface. Features resembling pingos, ice-driven mounds known from Earth and Mars, suggest additional interactions between subsurface ice and geology. Yet, Ceres shares the asteroid belt with vast numbers of other objects. Its gravity never came to dominate that region. Under the current definition, this keeps it within the dwarf planet category. The distinction describes orbital dynamics. It says remarkably little about geological complexity. That becomes clearer when we compare worlds across the solar system. Some moons possess atmospheres, oceans, volcanoes, magnetic interactions, and complicated internal structures. Certain dwarf planets have moons and active surfaces. Small bodies can preserve chemistry that larger planets erased long ago. Nature distributes these properties, across categories humans created for practical classification. Those categories remain useful. Without them, discussing thousands of objects would become cumbersome, but you can think of them as coordinates within a continuum rather than ranks on a ladder. The continuum begins with microscopic dust. It passes through pebbles, asteroids, comets, planetesimals, dwarf planets, rocky planets, ice giants, and gas giants. Gravity gradually changes what matter can become as mass increases. At certain scales, objects round themselves. At others, interiors differentiate, atmospheres persist, or surrounding material becomes dynamically controlled. Our vocabulary developed much later. For most of recorded history, the known planets were simply the wandering lights visible without telescopes. Uranus expanded that inventory in 1781. Ceres complicated it 20 years later. Neptune followed in 1846. Pluto arrived in 1930. Discoveries beyond Neptune eventually revealed that Pluto belonged to a broad population rather than standing alone. The dwarf planet category emerged from that expanding census. It provided language for worlds massive enough to become round, yet embedded within larger populations of neighboring bodies. So, the lesson from tiny worlds is partly geological and partly conceptual. Complexity does not begin at the boundary marked planet. Oceans, chemistry, differentiation, satellites, rings, and geological activity can appear below it. When we study these smaller bodies, the familiar 8 planets become members of a much broader family of worlds, shaped by the same materials and physical laws. Scale has an unusual relationship with memory. In planetary science, becoming larger often means becoming less faithful to your own beginning. Gravity compresses interiors. Radioactive elements supply heat. Rock melts, separates, rises, sinks, fractures, and sometimes returns to the surface in altered form. A world becomes more active, yet its earliest record grows harder to recover. Earth demonstrates this with remarkable efficiency. Plate tectonics continuously moves crust into the mantle while creating new crust elsewhere. Erosion reshapes exposed landscapes. Oceans dissolve minerals. Volcanoes bury older surfaces beneath younger ones. After billions of years, almost none of Earth's original crust survives for us to examine. Smaller bodies follow another path. Their interiors generally lose heat faster because they have more surface area relative to their volume. Many eventually become geologically subdued. Once that happens, ancient material can remain close to the condition in which it formed. Ice becomes a storage medium. Craters become timestamps. Primitive molecules remain embedded where later geology never reached them. Arrokoth gives this principle a physical shape. Roughly 22 miles long, it consists of 2 lobes that joined during the solar system's infancy. Their encounter happened at extremely low speed, more like a gentle settling than a destructive collision. 4.5 billion years later, that structure remains recognizable. Its value comes from what never happened afterward. No global melting reorganized its interior. No oceans repeatedly altered its surface. No system of moving crust erased its earliest architecture. When New Horizons passed Arrokoth in 2019, we were examining matter assembled near the beginning of planet formation and preserved with extraordinary fidelity. You can find similar lessons throughout science. Tiny isotopic differences inside meteorites reveal ages older than Earth rocks can usually preserve. Microorganisms around hydrothermal vents transformed ideas about where ecosystems can survive. The cosmic microwave background, a faint remnant of the early universe, preserves information from roughly 380,000 years after the Big Bang. In each case, significance arrived through something easily overlooked. That changes how we might think about the smallest worlds. Their importance does not depend on towering mountains, thick atmospheres, or planetary size. Sometimes scientific value comes from having experienced less. A large world can tell us what matter becomes after billions of years of transformation. A small, preserved body can carry evidence of what that matter was before the transformation began. We need both perspectives to reconstruct origins. So when you picture these distant objects, their modest dimensions can be misleading. They occupy little volume, reflect little sunlight, and often appear through telescopes as unresolved points. Yet within their ancient ice and rock, time has left unusually legible handwriting. The smallest worlds endure as records precisely because so much passed them by. Discovery often begins with an act that looks inefficient. Telescope time is limited. Spacecraft cost billions. Surveys consume years of patient work. Every observation, therefore, carries an implicit choice about where attention should go. The tiny worlds have repeatedly rewarded choices that seemed uncertain. Jane Liu and David Jewett spent years searching beyond Neptune. Conventional expectations offered little encouragement. Then, in 1992, they identified the first recognized Kuiper Belt object beyond Pluto and Charon. Their persistence helped transform an apparently sparse frontier into a vast population of icy bodies. Sedna arrived through another systematic search. When Mike Brown, Chad Trujillo, and David Rabinowitz announced it in 2004, its orbit refused to fit comfortably inside familiar explanations. The survey had been designed to find distant objects. What it uncovered instead was evidence that our map of distant orbital architecture remained incomplete. Ceres required a different kind of commitment. The Dawn mission launched in 2007 after years of development, cancellation, reinstatement, and technical pressure. By the time Dawn entered orbit around Ceres in 2015, its cameras could examine details unavailable from Earth. Bright deposits became landscapes. A crater became a geological laboratory. Features once compressed into distant pixels could finally be connected with salts, water-rich materials, and recent activity. Sometimes opportunity matters just as much. After New Horizons completed its Pluto encounter, engineers still had a functioning spacecraft and enough propellant for another target. Yet no suitable destination was known. The Hubble Space Telescope searched the spacecraft's reachable corridor and found Arrokoth, then known only through a catalog designation. New Horizons reached it on the first day of 2019. Think about the chain required for that encounter. A mission built for Pluto survived its primary objective. Engineers preserved enough capability to continue. Astronomers searched a narrow patch of sky. One faint object happened to occupy an accessible trajectory. Humanity then obtained close images of a primordial body nobody knew existed when the spacecraft left Earth. That pattern tells us something about exploration itself. Progress does not always follow a straight path from prediction to confirmation. Instruments improve, surveys widen, and observations expose details that force theories to change. An unexpected result can be scientifically richer than the expected one. The Vera C. Rubin Observatory extends that tradition through repetition and scale. Its decade-long survey is designed to record the southern sky again and again, revealing moving objects through accumulated observations. We cannot specify everything those observations will contain. That uncertainty is part of their scientific value. When you search deeply enough, nature gets room to answer questions we had not yet learned to ask. A familiar diagram of the solar system usually ends soon after Neptune. The planets appear neatly spaced around the Sun, with an asteroid belt inside and a band of icy objects beyond. That picture is useful for classrooms. In physical scale, however, it represents only the central neighborhood of something enormously larger. Past Neptune, orbital structure becomes increasingly diffuse. The Kuiper Belt gives way to the scattered disk, where objects travel on stretched and tilted paths. Farther outward, the Sun is thought to hold the inner and outer Oort cloud, an immense population inferred largely from long-period comets. Its most distant members may travel tens of thousands of astronomical units from the Sunday. We have never directly mapped that cloud. Models suggest it could contain trillions of icy nuclei. Some may be modest fragments, others could be substantially larger, because our present observations cannot inventory such a remote population. At those distances, sunlight becomes an exceptionally weak tool for discovery. An object can remain gravitationally bound to the sun while reflecting too little light for present surveys to identify easily. Time changes there as well. Near Earth, we measure orbital motion in years. In the remote Oort cloud, a journey around the sun can require millions of years. Galactic gravity also matters. The collective gravitational field of the Milky Way can perturb distant cometary orbits, while passing stars may alter them further. Occasionally, one of those ancient bodies is redirected inward. Its descent can span thousands of years. Consider what that means from our human perspective. A comet visible tonight may have begun moving toward the planetary region before any living observer's recent ancestors existed. Its path records, gravitational influences, operating across distances where the sun itself becomes only one star among many in the surrounding sky. Against that scale, our observing history is extraordinarily brief. The solar system formed roughly 4.6 billion years ago. Detailed surveys of its remote populations belong mainly to the last few decades. Even the census of comparatively nearby trans-Neptunian objects remains incomplete. The uncertainty is measurable. More dwarf planets almost certainly await classification. Additional sednoids likely occupy orbits we have not sampled. The proposed Planet 9 remains unresolved, while alternative explanations continue competing with it. Each possibility reflects the same limitation. Our observations cover only a thin slice of the available space, brightness, and orbital time. So the solar system you can picture most easily is its populated center, where sunlight is stronger and motion is faster. Beyond it lies a gravitational domain whose architecture is still being reconstructed from scattered detections. We live inside a system older than Earth, wider than ordinary diagrams suggest, and only partly catalogued. Its outermost members move on timescales that dwarf recorded history. For now, much of our own celestial neighborhood remains known through traces, trajectories, and the rare objects that wander close enough for us to notice. At this moment, Arrokoth continues along an orbit no human eye can follow directly. More than 4 billion miles from the Sun, its two joined lobes remain together, their narrow connection surviving from an age before Earth had settled into the world we recognize. Its reddish surface carries material altered by radiation, yet its overall form still belongs to planetary construction's earliest chapter. Earth changed almost beyond recognition during that interval. Oceans gathered, continents shifted and fractured, life emerged, diversified, and transformed the atmosphere. Species appeared and vanished. Eventually, one lineage developed instruments capable of detecting a body whose existence had gone unnoticed through the entirety of human history. Arrokoth continued around the Sunday. Elsewhere, Ceres follows its path through the asteroid belt, carrying salts and ancient water-related chemistry beneath a battered surface. Haumea completes another rapid rotation, maintaining the elongated figure imposed by its extraordinary spin. Makemake travels with its small moon through the distant Kuiper Belt. Their motions require no observer. Sedna follows a slower clock. Its enormous orbit lasts roughly 11,400 years, carrying it across distances that separate one close approach from another by the span of entire civilizations. Its next perihelion, the closest point to the Sun, arrives around 2076 according to current orbital calculations. By then, generations of observers will have inherited the questions attached to its unusual path. There is an important distinction here. These worlds were never concealed in any deliberate sense. Their faintness came from distance, size, surface reflectivity, and the limits of our technology. The difficulty belonged to observation. Nature had already placed the evidence where it would remain. For most of history, humanity lacked any way to retrieve it. Then photographic plates improved. Electronic detectors replaced them. Larger telescopes gathered more light. Space observatories escaped atmospheric distortion. Robotic spacecraft crossed distances once available only to mathematics. Each improvement expanded the portion of our own system that could become measurable. And still, our encounters are brief. New horizons passed Arrokoth in hours, gathering information from an object that had existed for billions of years before the spacecraft arrived. Dawn spent years at Ceres, then ceased communicating while the dwarf planet continued beneath it. Telescopes may watch Sedna across decades, yet that interval represents only a tiny fraction of one Sednian year. You and I live on a much faster scale. Our instruments are young, our surveys recent, our catalogs unfinished. Against the ages carried by these bodies, modern planetary science occupies little more than an instant. That may be the most fitting perspective to leave with them. The outer solar system never needed our attention to exist. Its small worlds kept their paths through every chapter of Earth's history. Only now have we learned how to notice them, and we have barely begun.